Even and odd symmetry in the polynomial functions by Dib. Contents. Welcome to my presentation on even and odd symmetry in polynomial equations. Today we'll explore how to identify even and odd symmetry in polynomial functions by analyzing the graphs and the equations. We will also focus on algebraic properties that define even and odd functions, and I'll demonstrate how these properties relate to symmetry. The goal is to understand how the different symmetrical manifest in functions and how to apply this knowledge to solve problems and identify patterns in algebra. Even functions. A function f(x) is even for every x in its domain. F negative x equals fx. This means that the function has mirror symmetry around the y-axis. Now let's look at the graphical interpretation. If you fold the graph of an even function along the y-axis, both havels will collide exactly. Even functions are perfectly symmetrical, reflected over the y-axis. Now let's look at some examples. fx equals x to the power of 2. The graph of fx equals x to the power of 2 is a parable that opens upwards and is symmetrical about the y-axis. Fx equals cos x. The cos function is periodic and exhibits symmetry about the y-axis. Algebraic properties. Even functions include terms with even powers. These terms involve no odd powers or combinations of odd powers. Example, x to the power of 2, x to the power of 4, x to the power of 6, and so on. Now I give you an equation example here. Fx equals 2x to the power of 4 plus 3x to the power of 2 plus 7. All terms here are even powers of x, making an even function. If you look at the equation and analyze it, 2x to the power of 4. 4 is a even number. 3x to the power of 2. 2 is an even number. So as we could tell, this is an even function. Odd functions. A function is fx is odd if every x in its domain f negative x equals negative fx. This means that the function exhibits rotational symmetry about the origin. Now let's see the graphical interpretation. If you rotate the graph of an odd function 180 about the origin, the graph will look exactly the same. Odd functions display symmetry when rotated, unlike even functions, which are symmetrical about the y-axis. Now let's look at some examples. Fx equals x to the power of 3. The graph of fx equals x to the power of 3 shows rotational symmetry about the origin, with the curve extending in both directions. Fx equals sine x. The sine function is odd and its graphs shows rotational symmetry about the origin escalating between positive and negative values. Algebraic properties. Odd functions are only terms with odd powers of x, and consistent solely powers such as x to the power of 3, x to the power of 5, x to the power of 7, and so on. Now if we look at an example I've given you, fx equals x to the power of 4 minus 4x to the power of 1. This function is odd because all the terms are odd. All the powers are odd. So as we can see, fx to the power of 3. 3 is an odd number. Fx to the power 4x to the power of 1. This is an odd number. So as we can tell, odd powers equals odd functions. Symmetry test. Even functions test. To determine if function is even, substitute negative x into the function and check if the result equals the original function. Example, check if f negative x equals fx. Now let's do the same or similar test to odd functions. Determine if a function is odd, substitute negative x into the function, and check if the result is negative of the origin. Example, check if f negative x equals negative fx. So for even function, we need to test if it comes back to original function. For odd function, we need to test if it comes back negative. Graphical check. If the graph is symmetrical about the y-axis, then the function is even. The function fx equals x to the power of 2 passes this test as a f negative x for all x's. So it checks out and it's even. Graphical check. For the odd, if the graph has rotational symmetry around the origin, then the function is odd. The function fx equals x to the power of 3 passes this test as fx. F negative x equals negative fx for all x's. Algebraic properties of even functions. Even functions an even function contains only even degrees. These are terms that have powers like x to the power 2, x to the power 4, x to the power 6, and so on. Example 1. fx equals 4x power of 4 plus 3x to the power of 2 plus 2. This function is even because all terms have even powers. 4x to the power of 4, even. 3x to the power of 2, even. 4 and 2 are both even. Examples, x to the power of 4, x to the power of 2. These are all even, so we know this function is even. Example 2. fx equals 2 cos x. Cos is an even function because it's graph symmetrical about the y-axis. The property is reflected algebraically as well. So when we look at cos in a graph, this it is symmetrical about the y-axis. So we could always tell that cos means even function. Even function and cos, they go hand in hand together, so we know they're together. So cos function is always an even function. Now let's look at the algebraic properties of odd functions. Odd function contains only odd degrees, such as x to the power of 3, x to the power of 5, x to the power of 7, and so on. Now let's look at example 1. fx equals 3x to the power of 3 minus 2x. This function is odd because both terms involved are odd powers of x. 3x to the power of 3, 3 is an odd number. 2x to the power of 1, 1 is an odd number. Now let's look at example 2. fx equals sine x. The sine function is an odd function and demonstrated by the fact that in negative x equals negative sine x. So as we could tell, a sine function is always odd. So when you see an odd sine function and an odd function, they go hand in hand. And just by looking at the graph, if the equation is sine, we can know it's odd. Graphical representation of even and odd functions. Even function graph. Function fx equals x to the power of 2. Now let's look at the graph description. The graph of fx to the power of 2 is a parable that opens upwards and is symmetrical about the y-axis. Visual aid. Show the graph of fx equals x to the power of 2, demonstrating symmetry about the y-axis. Now let's look at odd function graphs. Function fx equals x to the power of 3. The graph description to the graph of fx to the power of 3 shows rotational symmetry about the origin. It passes through the origin and extends in both positive and negative directions. Now let's look at the visual aid. Show the graph of fx to the power of 3 demonstrating the rotational symmetry. So what do we get from this? So if we look at even functions, if it's symmetrical about the y-axis, we always know it's even. If you look at the visual aid that I provided, the graph of fx to the power of 2 demonstrates symmetry about the y-axis. Odd numbers, if it has a rotational symmetry about the origin, then we know it's odd. If you look at the visual aid, demonstrating rotational symmetry means odd. This is how we can tell the difference between even and odd. Now, conclusion. In summary, we've learned how to identify even and odd symmetry in polynomial functions through both algebraic tests and graphical interpretations. Key takeaways. Even functions exhibit symmetry about the y-axis and have even degree terms. Odd functions exhibit rotational symmetry about the origin and have odd degree terms. Symmetry tests involve substituting negative x into function, checking if it satisfies the conditions of being odd or even. This knowledge helps graphing, analyzing, and understanding the behavior of polynomial functions. Thank you for listening to my presentation.